One of the most important experiments in the history of physics is the Young experiment, which shows, without a doubt, that light is a wave. We'll talk later about experiments that show that light is a particle. So there's a duality here, and Young's experiment is half of that duality. What is it? Got a source of light. The important thing is that the light passes through a double slit. So this is a piece of cardboard that you cut with some scissors, two slits that light can pass through. And then what you see on the far screen is not two bright spots on the far screen. That's not what you see. What you see is bright, dark, bright, dark, bright, dark, with the bright fringes, the bright regions called bright fringes, and the dark called dark fringes. But they repeat themselves. It's not like if you have a shotgun and you shoot at these two openings, you have a piece of metal and two openings in the piece of metal, what you'll see on the far screen is a bunch of shot in two different places. That's not what happens here. You get these alternating dark and bright fringes. Why? This looks a lot like some problems we did in chapter 17. If we define delta L as L2 minus L1, and remember, for constructive interference, that's supposed to be m times lambda, where m is an integer. It could be 0, 1, 2, 3, etc., etc. Well, in this case, delta L, if L2 equals L1, then L2 minus L1, which is delta L, is 0. That coincides with m equals 0, and we get a bright fringe, or in other words, constructive interference. In this case, delta L is L2 minus L1. In this case, it will be equal to lambda. That coincides with m equals 1. Also a bright fringe and constructive interference. What about this guy here? Delta L, the difference in path lengths, is 1/2 the wavelength. Well, that fits the delta L is m plus 1/2 lambda with m equals 0. And delta L, therefore, is 1/2 of the wavelength. And we get a dark fringe and destructive interference. So that's really the essential physics for what's going on here. As we continue to move further and further along this screen, we'll get a central bright fringe, then a dark fringe, then a bright, then dark, then bright, then dark, as we go through different amounts, different number of wavelengths by which the path length difference is. So, so this is what we see on the screen at the very central point. This is the m equals 0, the symmetric point where delta L equals 0. Path length, path lengths are both the same length. You got m equals 0, you got a bright spot. Then a dark fringe here. We're looking at the values of m for bright fringes. So this is a bright fringe, bright fringe. This is m equals 1, m equals 2 for these bright fringes, etc. So if we actually plot the brightness of the light as a function of distance along here, you'll see a really bright fringe in the center. The two m equals 1 fringes are a little bit less bright, etc. So let's derive the angular condition for bright and dark fringes on a distant screen for two slits separated by a distance d. Okay. Source 1, source 2, separated by a distance d. That's the center of slit 1 to the center of slit 2. All right? and we want a distant screen. So if we think of this distance to the screen, from the slits to the screen, as being large compared with the size of this slit width, then we're going to take that screen way over there, and these slits are close together. Then the two lines that are actually leaving here and going out to converge at a point on the screen, they look parallel to each other as long as this distance to the screen is large compared to D. So this is an approximation, but a very good one that will also makes the algebra a whole lot easier. So then if we blow up this little portion of the diagram here, those are path length L1 to the screen, path length L2 to the screen. The difference between the path lengths is going to be this little delta L right here. From then on out, they're traveling parallel, essentially parallel to each other. They get closer and closer and closer and closer, and then they match up when they hit the screen. So from here to the screen and from here to the screen, it just looks like an isosceles triangle getting closer and closer and closer. So here's where the action is. And in fact, the action is really, really easy to deal with. If this is D, the slit separation, and this is delta L, which is L2 minus L1, then we can look at this triangle and relate D to delta L. Well, this is a right angle here, and this angle theta is equal to this angle theta here. So that angle theta measures the angle of that line from the first path, from S1 to the screen, and also by similar triangles. This triangle here is similar to this one here, then that angle must also be theta here. And the sine of the angle theta is the opposite sine opposite, the side opposite divided by the hypotenuse. So sine of theta is the side opposite, which is delta L, divided by the hypotenuse, which is D. And you might be saying, well, hang on, isn't this red line here the hypotenuse? And I say, no, here's the right angle. So the side D is actually the hypotenuse. So sine of theta is delta L over D, opposite of a hypotenuse, and therefore delta L, well, then what we're going to do is to take that guy and insert it into concept 27-1. If you want constructive interference, remember, delta L, which is L2 minus L1, is m times lambda. So I'm going to substitute that, delta L, into here. And we got delta L is equal to m lambda. So I'm going to substitute m lambda in here for delta L, and we'll get m lambda over D. So that's exactly what we get here for constructive interference. The sine of the angle is m times lambda over D. Comes straight out of concept 27-1. Same thing happens for destructive interference, for dark fringes. Comes straight out of concept 27-1. For that one, we had delta L, L2 minus L1 is m plus a half times lambda. But we still have the same relationship for sine of theta. So we're going to put m plus a half times lambda in here for delta L. And we get the sine of theta is m plus a half times lambda over D. So it's essentially the same thing with a little bit of extra algebra added in. And m equals 0, 1, 2, 3, etc. Same as before. So notice and this is going to be a key for doing several problems. An example we'll do right now, and then problems as you think about it, to start to get a feel for the physics of how this works. Let's just look at this equation for starters. The sine of the angle, as you start from theta equals 0 and you get larger and larger, the sine also gets larger. So you just think about this as just having this be theta over here. It works well enough for these kinds of arguments. If you increase lambda and keep everything else the same, keep m and d the same, then theta is going to increase. And what does that mean? If we increase the wavelength of the light that we're passing through these slits, then the angles for constructive interference are going to get farther apart. That says that increasing lambda increases the separation between bright fringes. So if we were to increase the wavelength, then what we'd see over here, here's the 0th bright fringe, here's the next bright fringe, etc. These would be moving away from each other. They get more and more separated. And we'll see that in a demo coming up as well. If we increase the wavelength, actually, what we'll actually see in the demo is this guy here. So let's talk about him. Increasing D. So now we're interested in increasing the slit width. What happens then? If the slit separation, not the slit width, the slit separation increases, D is increasing here. So this right-hand side with D increasing is going to be decreasing. So the angle, the separation between those bright fringes is going to decrease. So increasing D decreases the separation between bright fringes. So what does that mean? If we increase the separation between these two slits, then these guys, the bright fringes, are going to come closer together. That's the key point. You increase this, you decrease the distance between the fringes. You decrease the D, you'll increase. They work opposite with each other. All right, let's take an example. In a Young's double-slit experiment, green light is incident on two slits, and the resulting interference pattern is everywhere on the screen. Which two of the following changes would cause the fringes to be spaced further apart? All right. We want to increase the distance between the slits. Well, what does that do? If you increase D, you will cause the fringes to be closer together, not further apart. So that doesn't give us what we want. But decreasing the distance does between the slits will get more separated fringes. So that's one way to do it. Decrease that distance, just like we talked about before. Use orange light instead of green light. This is a great question. Remember the diagram for, and you all memorized it. We had red on this end, violet on this end, and red was about 700 nanometers. Violet was about 400 nanometers. Green is somewhere in the middle here at about 500 nanometers. All right. So we're interested in orange light or blue light. Where's orange? Well, it's red and then orange. Roy G. Biv, right? So orange will be somewhere here. Is its wavelength greater or less than green light? You say, well, we're moving from green, which is maybe 500, over toward the red, so the wavelength is greater. So the orange light has larger wavelength than green. So if we increase the wavelength going from green to orange, then what happens? Well, back to here, if we increase the wavelength, that's exactly this case here, it will increase the separation between the bright fringes. It'll put them further apart. So this will also lead to more separated fringes. So blue light, what about that? Well, this is violet, so blue is right about here. It's between green and violet. That's decreasing the wavelength instead of increasing it. And so that has the opposite effect. That's not going to work to get the fringes that are spaced further apart. All right, a demonstration of double-slit interference done with the expertise of our amazing Media Productions team. This is a demonstration of the pattern you get when you send light through two slits. In this demonstration, I've got a laser here. I'm sending it through two slits that are separated in the first case by 0.25 millimeters, and then in the second case by 0.5 millimeters, larger separation. In both cases, each of the two slits is 0.04 millimeters wide. So what you see now is the pattern produced by this two-slit pattern. And you can see a big bright spot here, but I'm hoping you'll be able to see that there are small divisions, maybe 10 or 12 divisions within this big bright spot. Those are produced by the fact that we have two slits, interference, both constructive interference and destructive interference through this region. You can also see it divided out here in the other bright spots. So if we move to doubling the separation to 0.5 millimeters, then a wider separation means tighter spacing between those interference fringes. So you may or may not be able to see on the screen now that this main maximum is still as wide as it was before, but there's double the number of individual divisions within it. So the actual pattern that you can see right now is this single slit diffraction pattern for a single slit of width 0.04 millimeters, and then the divisions within that pattern that I think we'll be able to clearly see on this one is the result of the double slit pattern. Okay, I mentioned that this pattern is actually the superposition of two patterns. The double slit pattern, which are those fine divisions, bright, dark, bright, dark, bright, dark. And then the big bright regions are from single slit diffraction pattern. We'll talk about the single slit later. So the important part at this stage is understanding those tiny divisions. And as we talked about on the video, if you increase the separation between the two slits, then those fringes get closer and closer together. All right. An example, let's see. Red light is used in Young's experiment with slits separated by this tiny, tiny difference, tiny, tiny distance. 0.00012 meters. The screen is located at a distance of 2.75 meters from the two slits. Here's the slit separation. and we're supposed to find the distance on the screen between the central bright fringe and the third order bright fringe. Well, the central bright fringe is the m equals 0 fringe. The third order is the m equals 3. And we're trying to find this distance y. Well, one nice thing about this is that we can, from this triangle, see that the tangent of this angle here, the diffraction angle, or the interference angle, is the opposite over the adjacent. The opposite side is y. The adjacent side we're calling L here. And so that is shown, if we solve this for y by multiplying both sides by L, then that gives this equation here. We also have the condition for bright fringes, which we derived in the last concept, which is that the sine of theta is m lambda over d. So we can actually solve for theta by taking the inverse sine of both sides, and that gives us this equation, and then we just have to plug in the numbers. Remember that we're talking here about the third order fringe, this one here. So we're going to put in m equals 3. Then the wavelength we're given is 664 nanometers. That's 664 times 10 to the minus 9 meters. And then we're given the slit separation, which is 1.2 times 10 to the minus 4. So that gives an angle of 0.951 degrees. Once we have that angle, we can go back to this equation that we derived, plug in L, 2.75 meters, tangent of that angle, and that gives the actual distance, y, from here to here, to that image on the screen for the third bright fringe. So between here and here, we're going to have the m equals 1, m equals 2, and m equals 3 bright fringe. So there'd be a bright fringe here, m equals 1, m equals 2, and m equals 3, with a dark fringe in between each one of them, which we could have calculated as well if we wanted with the m plus 1/2. All right, so what if we do white light with Young's experiment? Then things get a little bit muddled because the angle for these bright and dark fringes depends on the wavelength. And white light consists of light of different wavelengths, between 400 nanometers and 700 nanometers. And so what you get is a separation of the light into beautiful colored fringes like this. And within each fringe, you'll see that the red is further away than the blue. Why is that? Well, we're talking about bright fringes now. If the wavelength increases, like we talked about before, then the angle will also increase, the position of that bright fringe. It'll be further away. So this might be the, looks like this is m equals 0, maybe m equals 1, 2, 3, maybe this is m equals 4 by now. Then the position of that bright fringe for red will be further away, the angle would be greater, and the distance will be greater on the screen. So that's why the red is further away than the green and the other colors. Why is the central fringe white? Well, because for the central fringe, we're using m equals 0. And so in that case, the angle doesn't depend on the wavelength at all because we multiplied the wavelength by 0. That's so cool. A couple of other ways that you can get interference. We're not going to do a lot of depth here, but I'd like for you to appreciate where you can see interference in nature. Ever spilled a little oil or gasoline on a wet pavement? You see something like this. This is called thin film interference, where you can see this is reddish. This is definitely greenish, yellowish, and it's repeating. There's red, 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 etc. like that, and then it goes back into violet and blue. Well, this looks like violet and blue in here. This is almost a violet. Anyway, you can see it's moving through the colors of the rainbow. How does that work? It works because the light that's shining on this little spot of oil on a wet surface, it only really works on a wet surface, and you'll see why in just a second. You've got air here, and you've got gasoline or oil that's sitting, it's lighter, so it sits on the top surface of the water, and then you've got water down below. But the indices of refraction of gasoline and water are different. And so what you get with incident light is a incident ray, reflected ray. That's number one here, that's reflected right at the interface between air and gasoline. And then you also get a refracted ray that goes down through the layer of gasoline, then reflects back off of the gasoline-water interface, comes through the gasoline-air interface and into your eye. So you've got two rays coming into your eye. Well, just like in double-slit interference, two-slit interference, those two rays can interfere with each other. And if the path length difference is a wavelength or a half a wavelength, with the wavelength, an integer multiple of the wavelength, you get constructive interference, etc. And so there's also some reflections and things we won't worry about here, but I think you got the basic idea. But because of the extra distance traveled for ray 2, ray 1 doesn't go as far as ray 2 does. It bounces right off that first air-gasoline interface. Ray 2 has to go through the gasoline twice, once to go down, once to come back up. Those two can interfere with each other, and that interference depends on the wavelength. And that's why you get these. So basically what you're seeing as you move through these fringes is changing thickness of that gasoline or oil layer. You can also see that in soap bubbles, fringes, beautiful rainbow patterns caused by thin film interference. And in this case, you've got air, then a soap layer, and then more air. But that soap layer thickness can change, and depending on the wavelength, you get constructive or destructive interference. Also, you can do the same thing with a wedge formed by two pieces of glass, two glass plates, where in this case, it's the air between the two glass plates whose thickness is changing, and you get interference fringes due to the two rays that come out through this thin wedge of air. You can also do this in a circular way. You've got a bowl-shaped piece of glass. You put it on a surface. You can see these circular fringes in this case. A Michelson interferometer also uses interference fringes. And the way that it works is you have some source of light that passes through a partially coated mirror. So some of the light gets reflected up off of the mirror and goes up this way. Hits a mirror up here, reflects off the mirror and comes back. Then the other ray of light goes through this thin silver coating over this other way, reflects back, and then they two get combined, wave A and wave F. So you can think of this as wave 1, wave 2. And when they come back here, if the path length difference, if path 1 here, or A, is different from the path F, then you can get constructive or destructive interference based on whether it's an integer or a half integer wavelength difference. And that gives you an extremely precise measurement of the difference in the distances between this mirror and this mirror compared with this mirror and this mirror. It doesn't give you the actual distance, but it gives you the difference in these two, in the distance, this distance minus this distance. This is how a very, very sensitive interferometer was used. It's called LIGO, the Laser Interferometer Gravitational Wave Observatory. In September 2015, LIGO, this interferometer, actually two interferometers in two different locations in the United States, were used to detect gravitational waves. tiny warpages in this fabric of space-time that Einstein predicted 100 years ago. And it was one of the most remarkable discoveries of all of physics, and it was made with an extremely sensitive interferometer that as the gravitational wave would pass, if it's passing this way, that would change this distance slightly, and the interferometry was used to detect that slight change in the fabric of space-time. Those gravitational waves match what would happen between two black holes when they merge together. So if you take two black holes, extremely powerful gravitational energy going on there, they merge and they send off like an explosion of gravitational waves that propagates out into space.